What if you could cut a large language model's height completely in half, but give it an iterative, exact memory of its own internal reasoning?
Yeah, that's exactly what we're getting into today. It's a really fundamental mechanical shift.
Right. Because for years, the golden rule of transformers has been completely structurally rigid. If you want deeper temporal reasoning, you have to stack more layers. Depth basically equals intelligence.
Exactly. That's the baseline assumption everyone operates under.
But today, we are looking at research that completely shatters that assumption. And if you are listening to this, you're likely navigating the bleeding edge of machine learning and data science.
Yeah, we designed this deep dive specifically for your technical background. We're looking at a paper called The Recurrent Transformer, Greater Effective Depth and Efficient Decoding by Oncescu and their team.
Right, and their core mission, what they've actually done, is modify the standard causal transformer to achieve unbounded temporal depth through layerwise recurrence.
And importantly, they managed to do this without triggering the gradient explosions that normally ruin recurrent models, all while preserving the hardware efficiency you absolutely need for modern autoregressive decoding.
Which is huge.
Hmm.
So the parameters for today,
Uh,
we're going to strictly unpack the architectural changes. No speculation, no artificial metaphors. We're looking at the mathematical proofs of stability, the hardware-level tiling algorithms, and the final empirical results on C4 pretraining.
Sounds good. We should probably jump straight into the core problem first, which is the temporal shallowness of the standard transformer.
Let's do it, because to understand the fix, you have to look at how a standard causal transformer moves information, right?
Right. So in a standard setup, when you are at a specific layer, let's just call it the current layer, and you are processing a specific token position, the attention mechanism obviously looks backwards.
Yeah, it looks at the past contact.
Exactly. But it only looks at the key and value pairs generated from the output of the previous layer.
Right, it's a strict sequential dependency. The tokens at layer 5 can literally only attend to the representations created at layer 4.
Yes. Which means if you want a piece of information to be processed, combined with other tokens and then reevaluated, it has to move up the layers.
It takes one full layer of depth to perform just one step of temporal reasoning.
Exactly. Which means your temporal processing depth is absolutely capped by your layer count. You can't go deeper than your stack.
Right, and the recurrent transformer introduces a highly specific structural change to break that cap, doesn't it?
It does. Instead of computing the key value pair for a token based on the previous layer's output, it computes that key value pair based on that token's output at the current layer.
Okay, wait, let me make sure we are visualizing this correctly, because that is a massive departure from standard architecture.
It really is.
So instead of a purely parallel feed-forward pass where everything just looks at the layer below it, a later token in the sequence is now attending to a representation of an earlier token that has already undergone attention and MLP computation within that exact same layer.
That is the layer-wise recurrence right there. Every single layer basically becomes its own distinct recurrent environment.
Oh, wow. So it's not like the older feedback architecture.
No, not at all. The model isn't sharing a single global memory state across all layers. Each layer maintains its own isolated key value memory, and that gets updated sequentially as you move across the tokens.
But wait, this introduces a massive structural circularity. AutoGrad should theoretically just throw a deadlock error here, shouldn't it?
You would think so, yeah.
Because if the model needs the final layer output for a specific token to create its persistent key value pair in the cache, how does it evaluate the attention for that token in the first place?
Right, you need the output to build the memory, but you need the memory to get the output.
Exactly. To get your final output, you need the attention mechanism to do its job. But the attention mechanism is waiting on that exact same output to build its memory. It's a classic computational cycle.
It is a literal cycle in the compute graph. And the way the authors resolve it is actually quite elegant. They split the concept of a key value pair into two distinct types.
Okay, what are they?
They define temporary and persistent key value pairs. So when the model is processing a token, it first computes a temporary key value pair using the input from the previous layer.
Which is exactly the way a standard transformer operates.
Precisely. It uses that temporary pair strictly to satisfy the local requirement for the attention mechanism at that specific token.
I see. So it uses the temporary pair just to compute the attention output for the current position.
Yeah, and then that attention output passes through the residual connection and the MLP block. That generates the final, fully processed layer output for that token.
And once that final output exists, what happens?
Once it exists, The model takes it and computes the persistent key-value pair. This persistent pair is what actually gets written to the cache for all future tokens to look at.
Ah, and the temporary pair.
The temporary pair is simply discarded. It did its job.
That's fascinating. And a really important detail from the math here is that the model reuses the exact same projection matrices, right?
Oh, yeah, that's a crucial point.
Like it uses the exact same weights for the keys and values for both the temporary and the persistent pairs.
Which is just brilliant from an engineering perspective. By reusing those projection matrices, you preserve a shared semantic consistency.
Because the temporary pairs and the persistent pairs are living in the exact same mathematical space.
Exactly. And you achieve all of this without introducing a single extra parameter compared to a standard transformer layer.
Okay, so we've solved the circularity problem by using these temporary keys, but I feel like that raises a much bigger theoretical question.
Which is,
Well, if we're bending the rules of standard attention this much and making the layer recurrent, what happens to the model's actual reasoning power? I mean, does it lose the representational capacity of a standard transformer?
it's a fair question, but the paper actually proves the exact opposite. Under mild assumptions, the recurrent transformer can perfectly emulate a standard transformer.
Really? Perfectly emulated.
Yeah, there is a specific proof theorem 8.1 in the paper that demonstrates this. It shows that a recurrent transformer of a certain width can simulate a standard transformer that is 1/3 its size.
Okay, how does it pull that off mathematically?
It does this by dividing its internal embedding space into 3 disjoint blocks, specifically a carry block, a live block, and a scratch block.
Let's break down what those blocks are actually doing in the matrix multiplications. Because an embedding space isn't just, a free-for-all.
Right. They have to organize the parameter space very carefully. So the carry block acts as a protected memory. It stores a pristine copy of the layer's input.
Which guarantees that when the persistent key-value pairs are computed later, they can perfectly track what a standard transformer would have seen.
Exactly. Then you have the live block, which holds the ongoing activation that will eventually go to the next layer.
And the scratch block.
The scratch block is isolated to hold the new attention contributions. That ensures the residual additions don't corrupt the protected carry memory we just talked about.
Okay, so by partitioning the embedding space, it completely retains the full prefix per token memory capabilities of a standard transformer.
Yes, but it also gains something new. It gains the ability to do token-to-token recurrent computation.
Right, because if the attention mechanism concentrates its weights locally on just the previous token, this architecture effectively implements a recurrent state space update, just iterating over the sequence.
Which positions this architecture in a really interesting middle ground. It can utilize fully parallel attention when it needs to look far back in the context.
But it can also execute purely recurrent, step-by-step state updates within a single layer.
Exactly. It's highly flexible.
But this brings up the ghost of classic machine learning. I mean, if this architecture is executing iterative token-to-token recurrent computation within a layer, why doesn't it suffer from the vanishing or exploding gradient problems?
Oh, yes. The classic RNN curse.
Right. We've all tried training traditional RNNs on long sequences. The gradients either vanish into nothing, and the model learns literally nothing, or they just explode into nans.
Yeah, backpropagation through time usually requires heavy gating mechanisms like LSTMs just to survive.
Exactly. So how does this model survive?
This is where the paper's path-based stability analysis is critical. Think about the physical bottleneck in a traditional RNN.
Oh.
Information moving from token position 1 to position 100 has to pass through a single sequential chain of 99 matrix multiplications.
Right. Every single piece of information is squeezed through that one temporal tube,
Yeah.
which is why the gradients compound and blow up.
But the recurrent transformer isn't doing that. It maintains the direct one-hop attention paths of a standard transformer.
So token 100 can just look directly at the persistent memory of token 1.
Exactly. It has those direct one-hop paths, but it also has multi-hop paths.
Because token 1 influences token 2, which updates the persistent memory for token 2, which token 100 might then attend to.
Right, you have this massive web of intersecting paths varying length.
So how do they mathematically prevent that massive web of multi-hop paths from compounding and blowing up the gradients?
They rely on 2 main mechanisms. First, an RMS norm is applied directly to the final layer output before it is used to compute the persistent key-value pairs.
Okay, so that normalizes the magnitude of the vectors. It effectively puts a ceiling on how large the signals can grow, even after multiple recurrent additions.
Precisely. And second, they apply standard depth-wise residual scaling. They scale the updates by 1 over the square root of the layer depth.
Which keeps the variance of the network in a stable range.
Right. And the paper formalizes all of this in Theorem 4.1. They actually analyze the gradient expansion of a simplified recurrent transformer to prove it doesn't explode at initialization.
So they calculate the gradient of a late output token with respect to an early input token and show that the gradient sums over all these different permutations of paths.
Yeah, and as long as the maximum eigenvalue of the scaled value matrix is smaller than 1, the math perfectly holds. The gradients stay bounded.
And because the gradient is summing over these direct and indirect paths, you maintain a healthy, non-vanishing gradient signal, even when the longer multi-hop recurrent chains are naturally dampened by the normalization.
The empirical ablation studies in the paper verify this perfectly, actually. When they removed that RMS norm step we talked about, training became violently unstable at higher learning rates.
So normalizing the recurrent state before writing to the cache is strictly required.
Absolutely. Non-negotiable.
Okay, so the math is brilliant on paper, but we really have to talk about the elephant in the room here. Hardware?
Yeah, the hardware constraints are real.
Because theoretical representational power is completely irrelevant if the sequential nature of this recurrence just chokes a modern accelerator. If we evaluate this naively, during training or pre-filling a prompt, it's an absolute disaster for a GPU.
It is easily the most significant practical hurdle of the entire architecture.
Let's lay out why. To compute the persistent pair at position 10, you need the fully processed output of position 10.
Right, but that output depends on the attention mechanism aggregating over the persistent keys of positions 1 through 9. You are inherently forcing the GPU to process tokens sequentially.
So let's frame this using the roofline model of compute performance, because the problem is obvious. If you process sequentially, each new query token requires you to load a linearly growing prefix of passkeys and values from memory.
Which means you are loading O of n data just to perform O of n arithmetic operations.
Exactly. That is an arithmetic intensity of O of 1. And on an H100 GPU, which is incredibly flop-rich but memory bandwidth poor, an operation with O of 1 arithmetic intensity means your compute utilization totally flatlines.
You are entirely bottlenecked by high bandwidth memory traffic. It's essentially untrainable.
So how do they fix it?
To bypass that memory bottleneck, the authors introduce what they call an exact tiling algorithm. And the critical observation that makes this work is realizing that during the prefill phase, all the queries for the layer are known entirely in advance.
Ah, right. The queries only depend on the parallel layer inputs, which we obviously already have at the start of the layer.
Exactly. Even though the persistent key-value pairs have to be generated sequentially, one by one, the queries for the entire sequence are just sitting there ready to go.
So because we have all the queries, we don't have to wait and load the entire key-value prefix for one query at a time.
Right. Instead, the algorithm processes the newly revealed key-value pairs in chunks, or tiles. When a new tile of keys and values is generated, the algorithm immediately broadcasts it to update the attention accumulators for many future queries simultaneously.
Let's make that concrete for a second. Imagine we are processing a sequence. The naive sequential approach computes the keys for token 5 and 6 and just lets them sit in memory until token 7 asks for them.
Yeah, and then it loads them again when token 8 asks for them. It's constantly going back and forth to memory.
But the tiled schedule computes the keys for tokens 5 and 6, grabs that chunk, and says, let's immediately compute the attention contribution of these two tokens for query 7, query 8, query 9, and query 10 all at once.
And to make that mathematical aggregation actually work without losing precision, they leverage online softmax running statistics.
Which is the exact same mathematical trick that powers flash attention, right?
That's the one. For every future query, the algorithm maintains a running maximum logit, a running denominator for the softmax, and a running numerator vector.
So when that new tile of persisting keys arrives, the algorithm just rescales those running accumulators and adds the new tile's contribution.
The asymptotic gains from doing this are massive. By reusing the streamed key value tiles across multiple future queries, while they are already loaded in SRAM, the traffic to the high bandwidth memory is reduced significantly.
It goes from quadratic O of n squared down to O of n log n. Right?
Exactly. And that correspondingly raises your effective arithmetic intensity from O of 1 up to O of n divided by log n.
Wow.
The hardware profiling in the paper is striking. If you graph the naive implementation on an H100, the latency grows quadratically as the context length increases. It's totally unusable.
With the exact tiled implementation.
Latency scales nearly linearly. It perfectly matches the theoretical bounds while producing the exact same mathematical attention output.
But the algorithmic efficiency of the tiling schedule is really only half the hardware battle, isn't it?
Yeah.
Because you still have to interleave the multi-layer perceptron computations with these attention updates, which exposes a completely different lower-level systems bottleneck.
CPU dispatch latency.
Let's unpack that.
Well, because the MLP block now has to process a small batch of tokens at a time, as the sequence unrolls, say, a block of 512 tokens, rather than processing the entire sequence at once like a standard transformer, you are suddenly launching thousands of tiny, short-lived compute kernels from the CPU to the GPU.
Right, and the GPU finishes executing the math faster than the CPU can even send the next instruction. So the CPU dispatch overhead becomes the bottleneck on the critical path.
To eliminate this, the authors utilize CDA graphs.
Oh, nice.
Yeah, CDA graphs allow you to record the entire sequence of kernel launches the full forward and backward pass computation into a single execution graph.
So you dispatch that graph to the GPU once, and the GPU handles the sequencing internally without constantly waiting on the CPU.
The profiling data in the paper proves how vital this is. Without CUDA graphs, the training latency basically remained flat regardless of how small they made the token blocks. It was completely bottlenecked by the CPU.
But with CDA graphs, the latency scaled down proportionally with the compute cost.
Exactly. And there is one more critical systems-level optimization, specifically in the backward pass.
Right, because standard PyTorch autograd handles sequential recurrent operations very poorly.
Terribly. Specifically because it relies on operations that create new memory allocations, like concatenating tensors. That absolutely thrashes memory bandwidth when building the persistent cache sequentially.
So they had to write a custom backward pass.
They did. If you look at the dependencies during backpropagation, you really only strictly need to accumulate the gradients with respect to the persistent key value pairs sequentially.
Oh, I see. So everything else, the gradients for the input tokens, the queries, the temporary keys, and the actual model weights, none of that has an immediate sequential dependency across the sequence length.
So they decouple them. They process the strictly sequential gradients in a tight loop and then compute the rest of the gradients outside that loop using massive batched kernels.
Which completely maximizes parallel compute utilization during backpropagation.
Right, and when you synthesize all of these mathematical stability proofs, the tiling algorithms, and the system optimizations, you finally get to the empirical results.
And the results show a definitive shift in the depth with Pareto frontier of sequence modeling.
Let's look at the C4 pre-training numbers at the 300 million parameter scale.
Okay, so they trained a baseline standard transformer with 12 layers and a model width of 1408.
Then they trained a recurrent transformer with only 6 layers, but they widened it to 2048 to keep the parameter count exactly the same. Both models have roughly 300 million non-embedding parameters.
And what were the results?
The 6-layer recurrent transformer outperformed the 12-layer baseline. It achieved a validation cross-entropy of 2.86 compared to the baseline's 2.896.
Wow, which proves definitively that layerwise recurrence allows you to trade depth for width without sacrificing any representational capacity or reasoning performance.
And we really need to spell out the mechanical benefit of that trade-off.
Right, because achieving equivalent loss with half the layers fundamentally alters the memory profile of the model during inference. It's all about the key value cache.
Exactly. The size of the KV cache during autoregressive decoding is proportional to the number of layers, multiplied by the number of attention heads, multiplied by the head dimension.
So if you cut the number of layers in half, you are directly having a massive multiplier in the KV cache equation.
Now, to maintain the same total parameter count, you do have to increase the width of the model.
Right, but parameter count scales quadratically with width, meaning you only need to increase the width by roughly the square root of 2, about 1.4 times to make up for having the layers.
So you have the layers, which is a 0.5 multiplier, but you only increase the width by a 1.4 multiplier. The net result is that the total size of the key value cache shrinks.
In this specific configuration, matching the 12-layer baseline quality with a 6-layer recurrent transformer reduces the key value cache memory footprint by roughly 30%.
And during autoregressive decoding, reading the KV cache from high bandwidth memory is the absolute primary constraint on token generation speed.
So a 30% smaller KV cache directly translates to 30% less memory traffic per token. That fundamentally improves inference efficiency.
It's massive.
The core takeaway here isn't just about saving memory, though. It's that we've been building taller and taller transformers for years, basically assuming strict layer depth was the only path to complex reasoning.
Yeah.
But this paper proves you can build structurally shorter models that essentially remember and iterate on their own thoughts, achieving the same or better reasoning power with half the layers.
Exactly. To summarize everything we've covered, first, calculating persistent key-value pairs from the current layer output breaks the temporal shallowness of standard attention. That allows multi-hop recurrent paths.
Second, the exact tiling algorithm, combined with online softmax statistics, completely rescues the architecture from sequential hardware bottlenecks. It raises the arithmetic intensity so it can actually run on modern GPUs.
And third, this architecture shifts the optimal depth-width ratio, yielding massive memory footprint reductions during inference.
It is just a rigorous validation that the bounded temporal depth of standard attention is a limitation we can engineer around without abandoning the hardware efficiencies that made transformers dominant in the first place.
It completely opens the door for new architectures.
Which leaves us with a fascinating theoretical asymptote to consider. If layerwise recurrence allows us to trade depth for width so effectively without losing representational power, what is the ultimate mathematical limit of this compression?
That's the real question.
Could future architectures eventually collapse into a single massively wide recurrent layer using dynamic lock scheduling to fully capture the reasoning capabilities of today's 100-layer autoregressive giants? We started by observing the strict structural boundaries of sequence modeling. The recurrent transformer proves those boundaries are highly permeable. Thank you for joining us for this deep dive into the source material, and we encourage you to keep questioning the structural assumptions in your own models.